We're finally to the end of the first unit. This is the last lesson in our first unit, and that is inequalities. Today we're trying to solve some linear inequalities, some compound linear inequalities, and some absolute value inequalities, and then try and apply those to some word problems. An inequality, the only difference in an inequality and an equation like we have been solving is the equal sign, right? So normally our equations have an equal sign. Our solution is just a number. With inequalities, we're not going to have that equal sign. We're going to have these four symbols: greater than, less than, greater than or equal to, less than or equal to. You should memorize those words now. With a greater than or equal to or less than or equal to, with an inequality, you're not going to get just that point. You're actually going to get a set of numbers, and if you look over here at these shaded areas, notice that all of the numbers shaded are solutions, right? And sometimes you'll have a closed circle, meaning that number's included. Sometimes you'll have an open circle, meaning that number's not included, but all the shaded numbers are included. We should make note of this as well. With both of the greater than or less than, we're going to use an open circle to notate on a number line. With a greater than or equal to or less than or equal to, we're going to notate that with a closed circle on the number line. Alex sometimes doesn't give you the option to use an open or closed circle. Sometimes they only give you the option to use parentheses or square braces, but that's how those match up. The parentheses always match up with just the less than, just the greater than. The square braces always match up with the greater than or equal to or the less than or equal to. So write that down in your notes now and save that for later. We're going to have to use that here in a minute. All right, these are all the different ways. We don't have to go through every single one of these ways that these will work out, but let's say, for example, we have the interval from a to infinity, right, with a parentheses on the a. That means the a is not included, and it's shaded all the way to infinity. We're going to get to more of this later. The right-hand arrow is a positive infinity. The left-hand arrow, as you see over here, is a negative infinity. You can see that notated. Anytime you go from a to b, either endpoint can be included or excluded. In this case, a is included because it has the square brace. That's the same thing as a closed circle. B is not included because it has the parentheses. That's the same thing as an open circle. It just depends on what Alex gives you the option to use. Again, when we get to solving these inequalities, you're going to see some more of this. To solve an inequality, we solve it just like an equation. There's only a couple of caveats, and we're going to see one of those caveats in this equation right here. So to solve this, we would subtract 4. We'd have negative 6x less than 30, and then we would divide by negative 6. And here's our first caveat. If you multiply or divide by a negative number, you have to flip your inequality sign. So whenever I divide x, I have to flip it anytime you multiply or divide by a negative number. This says first solve the inequality. We've done that. Next it says to graph the solution. So negative 5 lies somewhere on a number line between negative 4 and negative 6. Since this is strictly greater than, not greater than or equal to, we're going to use an open circle. We could use a parentheses if we wanted to. And since its x is greater than, we're going to shade to the right. I tell people that the greater than or less than, as long as your variable is on the left side of your inequality, that symbol is going to be an arrow to show you where to shade, right? If it was this way, it would be an arrow pointing that way to shade that way. That only works if the variable's on the left side, that arrow deal there. It says write the solution in set builder notation. All right, set builder notation, here's what it looks like. It always has a swirly brace. You're going to see this on Alex or Pearson as well. A swirly brace in the beginning and end, and a bar in the middle. It's always set up like that. In the first slot here is going to be whatever variable you were using. In this case, we were using x, so x is going to go in that slot. In the second slot is exactly what your solution was. X is greater than negative 5, and you want your x to be on the left side of that inequality. So here is our set builder notation. Check. We've solved, we've graphed, we have our set builder notation. Last up is interval notation. Interval notation, all we're going to do is describe what is shaded on the number line. Once you have it graphed, interval notation is easy because it's just shaded from negative 5 all the way to the right, which means to infinity. If you look back at that chart on the last page, infinity is always going to have a parentheses. Infinity will never have a bracket. And if you look back at the chart that I made you on the first page, if you have an open circle or if you have just strictly greater than, that's also going to match with a parentheses. So our interval notation will look like that. Let's do some more of these. I think the more practice you get, the better you get with these. Any with fractions, they're always going to work the same, and I think I've said this. You're going to approach fractions the same way every single time. To get rid of fractions, we're going to multiply by every different denominator. I don't like dealing with fractions. You don't like dealing with fractions, so let's just get rid of them, step one. And when you do that, you can get rid of the things that match up. Be very careful with this. You do need to keep up with what's still there, so 2 times 6 would be 12 times x plus 1, for example. The minus sign will come down. The inequality sign will come down. 2 times 3 is 6 times 2x minus 4. And 3 times 6 is negative 12. And we have still an x. Distributing in the 12 and the negative 6, you get this. Combining your like terms. Dividing by the negative 12, and don't forget when you divide by a negative, you have to flip that sign. You could put that on a number line, set builder notation, and your interval notation, this time it's shaded all the way from negative infinity to negative 3, right? We're always reading it left to right. It's shaded from negative infinity to negative 3. Negative infinity will never have a bracket. In this case, the negative 3, since it's a closed circle, and since our actual solution had that less than or equal to, we're going to use a square brace here. All right, solving compound linear equalities. They can have an and or an or between them. Typically, I'm saying typically, this is not always true, but typically if you have an or, you're going to be shading to the outside. Typically, you can make note of this, typically if you have an and, you're going to be shaded in between some things. These can be open circles, they can be closed circles, it doesn't matter which. The same thing up here, we can have open circles, closed circles, any of those are fine. But typically an or is going to be shaded on the outside. Typically an and is going to be shaded in the middle, but you do want to check. All right, with an or, if either one of those things are true, if this is true or this is true, then it's going to get shaded. So the first one, to solve, we add 2. X is less than or equal to 7. The second one, we can multiply by 2. X is greater than 12. This is an or. If either are true, then we're good. So the first one, x is less than 7. Less than or equal to 7. That's a closed circle, shaded less than or equal to 7. The second one, 12, open circle, shaded greater than 12. Remember I said or typically is going to be shaded on the outside, and this time that did happen. And our interval notation, it goes all the way from negative infinity to 7. And then it goes all the way from 12 to infinity. And if you ever have two separate intervals, that means we have two separate shaded areas, right? Two separate shaded areas. The way you're going to connect those is with a U, and that means union. Union means all of this plus all of that. All of those are answers. This is the answer that you're going to put in MyLab or Pearson. All right, this one says and. Remember with an and, typically you're going to shade in between some things, but we'll see if that's true here. The first one, we can multiply by negative 4. Multiply by negative 4. And what would happen is we would get just a regular 1t. Since we multiply by negative, we'd have to flip the sign, and we'd have negative 8. On this one, we can divide by 0.52, and I'm going to have to pull out my calculator for that. 1.3 divided by 0.52 gives me 2.5. So t is greater than 2.5. This is an and symbol, so both of them have to be true. We can color code this a little bit. And t is greater than, this is greater than or equal to, t is greater than negative 8. That goes here. And t is greater than or equal to 2.5. 2.5. That goes here. So the question is, where are both of those true? And they're both true here, right? They overlap in that zone. from 2.5 up, they overlap. And so our solution here is everything from 2.5 to infinity. With an and, you're looking for overlapping areas. In this case, they just both happen to, since we multiply by a negative, they both of the signs happen to flip the same way. A three-part compound inequality, this is another one where typically, again, this is just typically, you have an x sandwiched in the middle, you're going to have something shaded sandwiched in the middle. Let's see what happens. With a three-part inequality, you can break it off into three different pieces, okay? And whatever you do, like we typically say we have to add or subtract to both sides, you have to add, subtract, multiply, divide to all three of those different sections. So if I want to get x by itself, the first thing I can do is subtract 7. And I have to do it to all three places. So that'd be -2, keep the same sign, -2x, keep the same sign, 4. To get x by itself, I can divide by -2. We're dividing by a negative here, so be careful. A 1, flip our sign, x, flip our sign. Oh, I didn't flip that first sign, did I? I said it and I didn't do it. Flip our sign, a x, flip our sign, and a -2. I'm going to erase these dividing bars here now. Let's clean this up a little bit. So 1 greater than x greater than or equal to -2. So -2, if we put these on a number line, -2 is going to be on the left, 1 is going to be on the right, 0 somewhere in between. Here the 1 has just a less than, so the 1 is going to have an open circle. The 2 has a greater than or equal to, so the 2 is going to have a closed circle. And the x is sandwiched in between, so we're going to shade in between. You can check one of these numbers and make sure that it works. So 0, for example, is 0 less than 1? Is 1 greater than 0? Yes, it is. Is 0 greater than -2? Yes, it is. As long as it checks out with both sides, then it's good. And our interval notation here is everything from -2 to 1. The 1 is not included, but the 2 is. That's supposed to be a square brace. I apologize for my handwriting there. If you wanted this in set builder notation, you would do the same exact thing. We're solving for x, and we got this as our solution. We really need to reverse the order of those. You need them from smallest to biggest. -2 is smaller than 1, so we're going to say -2. Since I'm flipping it, I'm flipping everything, okay? Close my set. If you ever want to flip it around, you can flip it around. You just have to flip everything. You do typically want it from least to greatest. All right, absolute value inequalities. What happens with an absolute value inequalities? You're going to end up breaking it into two pieces. And again, you have some caveats where you automatically know that something either always is true or something always is not true. But if I have something like this, let's say I have absolute value of x less than 3. What I'm going to do is absolute value of x less than 3. I'm going to say first the same exact thing, x less than 3. And just like we did with absolute value equations, we're going to keep whatever's inside the absolute value, we're going to leave it alone. And everything else we're going to change, so greater than -3. If we solve both of those, we'll have our answer, right? So, oh, they're already solved, great. And then there's two keywords here, where if you have a less than, it's going to be an and. If you have a greater than, more, it's going to be an or. I always remember less than, and, more, or. Remember, with an or equation, almost always it's going to be shaded to the outsides. With an and equation, it's almost always going to be shaded in between. So on this one, this is an and, because it was less than. This is when you break it into two pieces, you're going to check this. So I broke it into two pieces. It's an and equation, right? So we know we're probably going to shade in between, but let's just check. We have -3, we have 3, 0 somewhere in between those. They're both going to have an open circle. Is 0 less than 3? Yes. Is it also greater than -3? Yes, we can shade there. Is -4 less than 3? Yes. Is it greater than -3? No, so it's not both. Is +4 less than -3? No, it already does not match the mold. Those numbers don't work. Numbers in here do work. And our interval notation is from -3 to 3. Let's try one of these. Just like with absolute value equations, it's easiest if you can get that absolute value by itself first. So start with adding the 3. Then we can divide by the 2. Then we can break it apart into 2 different equations. Since it's less than, we know it's going to be an and. And 6 minus m, less than 5. One exactly the same. 6 minus m. These are like a protective barrier. You're not going to change what's inside of those. But what's outside, everything is going to change. And we can try and solve these. Negative m is less than -1. If we divide both sides by -1, m is greater than 1. And on this side, subtract 6. M is less than 11. M is greater than 1 and less than 11. What numbers are greater than 1 and less than 11? Numbers like 5 are greater than 1 and less than 11. This is strictly greater than, strictly less than, so open circles, and we can shade in between. And our interval notation is everything from 1 to 11. Again, this is interval notation. Solving an absolute value inequality, the same exact thing. We can divide by the -2 on both sides, right? When you divide by a negative, that sign flips. You can break it into its 2 pieces. When you're trying to determine less than, greater than, more, or, and, that type of thing, it does help, or the only way that that mnemonic situation works is if the absolute value is on the left, right? It's the same way as your shading deal. You know whether to shade right or left based on whether, if X is on the left, where the arrow is pointing right, but the variable has to be on the left. Same thing here, to determine whether it's or and, that mnemonic, it helps, or it only works, I should say, if the absolute value is on the left side. So I just flipped the absolute value around. Again, I flipped everything, including that absolute value sign. All right, whenever we break it apart, 3x plus 1 greater than or equal to 2, or 3x plus 1 less than or equal to -2. We changed everything that was outside. Everything that was inside is in that protective barrier. We can solve both of those. Keep solving. Put that on a number line. Since it's or, we need to shade to the outsides. And that's what our interval notation looks like. There are some special cases, just like when we said earlier, an absolute value of x cannot be equal to a negative number. That was on the last lesson. You can't have an absolute value equal to a negative number. Here, you can't have an absolute value less than a negative number because an absolute value is going to turn something positive, and a positive can't be less than a negative. So if you ever end up with an absolute value less than a negative, this is going to be no solution. If you ever have an absolute value greater than a negative, this is going to be all real numbers. Because any number you turn positive is going to be greater than -4. If you ever have a number less than or equal to 0, absolute value less than or equal to 0, that's the same exact thing as saying it's equal to 0, right? Because it can't be less than 0. That would mean it's negative. So in this case, we could just set it equal to 0. If you ever have one that's greater than 0, let's just check this one out and see what happens. If we have one that's greater than 0, that means when we break it in half, this is a or. X minus 5 greater than 0, or x minus 5 less than -0, which is just 0. That means x is greater than 5, or x is less than 5. That means everything except for that number, right? This one's a very strange special case. So everything greater than 5 is over here. Everything less than 5, that's over here. But in neither of those are we including the 5, right? We're not including the 5. So our interval notation is actually negative infinity to 5, and then also 5 to infinity. All right, here's an application. Shanice has test scores. It gives us 5 of her test scores. Her score for her online homework is 100 and is weighted the same as an online test score. So we have 1, 2, 3, 4, 5 scores. Count this as a test, so that's 6 scores. She needs to take the final exam, which counts as 2 test grades. What score does she need on the final exam to have an average of at least a 90? An average of at least a 90 means greater than or equal to a 90. If we want to average those things together, you add everything up and divide by how many you have. So you have 1, 2, 3, 4, 5, 6, and then it says the exam score is worth 2 test grades. I'm going to have to adjust the way that I work this problem. So we have all the test scores added up. 1, 2, 3, 4, 5, 6. And then the exam is worth 2 of those, right? We don't know what the exam is, but it's worth 2 of those test scores. In all, we have 1, 2, 3, 4, 5, 6, 7, 8 things. So to find the average, we add them up and divide by 8. We want that average to be greater than or equal to 90, at least a 90. When you add them all up, you end up with that on top. You can multiply both sides by 8. You can subtract the 546, divide by the 2, and your score has to be greater than or equal to 87. If you get an 87 or better, you've passed with an A.